Good evening. I hope my screen is visible. So welcome to tutorial 9. So in this tutorial we are going to cover questions on Bode plot. So in this week 9 we have seen how we can plot the response of sinusoidal inputs. Okay. So in the previous week we have seen if we give a sinusoidal input to a plant, so what is the output, so what is the how the magnitude of the output changes and what is the frequency. Okay, so in this week we will be seeing the frequency response. Okay, so I will just cover what is what is covered in this week. Okay, so in the last week we have seen this. Okay, so if there is a plant transfer function p of s, if you put j omega, then we'll call it as sinusoidal transfer function. Okay, so an important result that we have seen is shown here. Okay, so this is it. So as you can see, so the final output has same frequency as input, and also you can see the magnitude is just scaled by the magnitude of input. Okay, p of j omega. Okay, and p of j omega is the sinusoidal transfer function. Okay, and how to find the magnitude? So we have seen a common representation of this sinusoidal transfer function. This is like numerator divided by denominator, so we individually take the magnitude. Okay, so as seen here, and how we take the angle, so it is similar to that. Okay, so here it shows the magnitude and the angle. So in this week we are seeing the Bode plot. So how to visualize this sinusoidal transfer function, okay, with respect to omega. So we'll be seeing the Bode plot. So in this week we have covered Bode plot for different functions. Okay, so when I say function means s 1 by s, uh, st plus 1, or 1 by st plus 1. Okay, so what is we'll be drawing two plots here. First is magnitude plot and other one is the phase plot. Okay, so these two plots will be with respect to frequency. Okay, so omega. So here magnitude, so if you see the y-axis, so it is in dB. Okay, so what is dB? dB is 20 log of, so this is log of 10. Okay, so we'll take the magnitude p of j omega, and we'll take the log base to the 10 and into 20. So this thing we are calling as dB, decibel. Okay, and if you see the x-axis, so instead of taking omega, we are taking log of omega. Again it is base to 10. Okay, base of 10. So why we are taking, so we have also seen, because we can cover, then if we take log of omega, then we can cover larger range of omega, and at the lower frequency range we can cover like low frequency range also. Okay, so that's why we took the log of omega. Okay, and also one of the benefits, if you see along the y-axis, if we are taking the log is, so this is the transfer function, so we can represent the magnitude of individual quantities in numerator and denominator if we take the log like this. Okay, so it is just summation and subtraction of individual magnitudes. So this is one of the advantage. Okay, so that we don't get in linear scale. Okay, so other is phase plot. Phase plot is just, we on the y-axis we are taking the phase in degrees, and on the x-axis we will be again taking log scale. Okay, so this we will be studying the building blocks, how to plot the magnitude and phase plot for common building blocks that we encounter, like a constant function, okay, a pole, a zero, okay, first order pole, okay, first order zero, and again second order. 0 and poles. Okay, so you'll be drawing the magnitude and angle plot for these building blocks. Okay, so first we have seen for the constant. So constant is just, if you can see j of j omega is constant, so it does not vary with respect to frequency. So if you see its magnitude plot, so magnitude plot is constant. Okay, so you can see here, this is the magnitude plot. Okay, and what is the angle is 0 degrees, so it depends on the value of k. Okay, so if k is positive, then we say the angle is 0, and if it is negative, then it is minus 180. Okay, so this is shown here. This is the simplest plot that we have seen here, and a few important terms we have seen. First is decade. So what is decade? So decade is like at a particular frequency, if you go above 10, like if you increase the frequency by 10, so this is a range like omega to 10 omega, so this we call as 1 decade, right? And similarly, another example is, this is 1 decade above omega, and if you take 1 decade below omega, then it will be from 0.1 omega to omega. Okay, so this all. So another thing is decade we have seen. One another is octave. Okay, so if we take this range omega to 2 omega, then we say this is a octave, so we can go above and below also. Okay, so again, what is the Bode plot for 1 by s? Okay, so that we have seen. So how to do that? So first you find the magnitude, so in terms of dB. Okay, this is how you find the magnitude. So first is you find the magnitude and you take the log of 20 log of 10. Okay, that's how we calculate the magnitude in dB. Okay, so this is shown here. Again, angle is very straightforward. Okay, so you can see this is how the magnitude and the angle plot look for this 1 by s function. Okay, you can see for 1 by s it is decreasing. Okay, the slope is decreasing by 20 dB per decade. So how to find what is the slope? You just take for a frequency of omega, just take frequency 10 omega and see what is the value at that particular frequency. Okay, so it is given here. So at 10 omega, what is the frequency? So just put 10 omega in 20 log of 10. Okay, so you'll get this quantity. So what we have seen is, as we have increased the frequency by 10, the magnitude has decreased by 20 dB. So what we are saying, this slope of this curve is minus 20 dB per decade. Okay, so when we are going 1 decade above, the magnitude is decreasing by minus 20 dB. Okay, so that's why we are calling this minus 20 dB per decade slope of this line. Okay, similarly you can find in octave also. Okay, so in octave, just take the frequency at 2 omega. Okay, so you will see minus 6. So that's why we are calling minus 6 dB per octave. Okay, so, and very easy to find the angle. Okay, this is minus tan inverse omega. Okay, so similarly, in this plot we have also plotted the g of s equal to s. Okay, so in this case the slope will be increasing by plus 20 dB per decade. Okay, and what is the magnitude? Sorry, what is the angle? Angle is plus 90 degree because it's a numerator. Okay, so what we have seen this. Okay, then we have seen the transfer function g of s equal to 1 by ts to s plus 1. Okay, where t is greater than 0. So it is like similar to this s plus a. Okay, just we are making the coefficient of just we want in this form. It can be also written as, if you take a common, s by a plus 1. Okay, so here t is what, 1 by a. So we want to convert into this one. Okay, simple. So again we take the magnitude here. So how we take the magnitude, that also we have seen in the previous weeks, and the angle. Okay, so here one important thing is we want to construct two asymptotes. Okay, at low frequencies and at high frequencies. Okay, so we want to find the magnitude in dB at these two frequency ranges. Okay, so how to construct that? So for the low frequency range, we assume that omega is very less than 1 by t. Okay, if you take omega to be very less than t, then if you see what is the magnitude is equal to 1. If you take log of 1, that would be equal to 0. So that's why it is shown 0 dB. So this is low frequency asymptote. Okay, correspondingly, if you take higher frequency range, so for the higher frequency range, what we are assuming is this omega is much greater than 1 by t. Okay, so that means if you see this, okay, t square omega is much greater than 1. Okay, so 1 can be neglected. Okay, so it will be 1 by root of t square by omega square. Okay, so that is written here. So if you take the log, you will get this value. Okay, so this is the high frequency asymptote. Okay, so now you can see we can directly plot with respect to omega. Okay, so here also for high frequency we can find the slope similar to what we have seen in the previous cases, 1 by s and s case. Okay, same thing. And what is the corner frequency? So at corner frequency, low frequency asymptote and high frequency asymptote intersect. Okay, that's what we are calling a corner frequency. So how to find the corner frequency? You see at see the high frequency asymptote, and you see at what value of that asymptote you'll get the low frequency asymptote. Okay, so what I mean to say is when this becomes 0 dB. Okay, so if you put omega equal to 1 by t, so log of 10 of 1 you'll get. Okay, that will be equal to 0 dB. So omega is your corner frequency. Okay, that we'll see in our questions also. Okay, similar to procedure is same to find the what is the slope of the function. Okay, so we have seen, but that is the asymptote. So how the actual curve differ from the asymptote, that we have seen. So what is the error? Okay, so you'll see the error is maximum at corner frequency. So 1 by t was the corner frequency, so you can see from here, so we get the maximum error. So as we go away from the corner frequencies, you can see now the error keep on reducing. Okay, so we can approximate the actual curve with the approximate curve. Okay, because the error is very small. Okay, that also we have seen. Okay, you can see the error here. Okay, so at 1 by t the error is maximum, and if you see the other points, the error will decrease. Okay, so here you can see the phase plot here. Okay, so similarly with the function gs equal to ts plus 1, so it will be opposite to that. Okay, so the low frequency asymptote will be 0 dB, and the high frequency asymptote will increase by 20 dB per decade. Okay, and the angle will be opposite to that. Okay, so in previous case, initially the phase initially it has my plus 90 degree, and I think not plus 90 degree, yeah, 0 degree, and it went to minus 90 degree at higher frequencies. So here you see it starts from 0 and goes to plus 90. Okay, then we have seen for second order functions. Okay, same thing for the second order function also. We are plotting low frequency asymptote and high frequency asymptote. So you can see here low frequency it's 0 dB, high frequency it's minus 40 log of omega by omega n. Okay, so this is the condition, right? So this is the condition. So when omega is very less than omega n, this is the natural frequency, you'll get the low frequency asymptote. Okay, and correspondingly, if omega is much greater than natural frequency, you can approximate the magnitude plot. Okay, so it is given like this. Okay, again, how to find the corner frequency? The procedure is same. Okay, you see at what frequency your high frequency asymptote is equal to intersecting low frequency asymptote. Okay, so in this case, if you put omega equal to omega n, the value is equal to 1, so log of 1 is equal to 0. Okay, so that is equal to 0 dB. So you know omega equal to omega n is the crossed corner frequency. So you'll see in the questions also. Okay, So how to find the slope? The procedure is same here also. So here we have seen when the magnitude is maximum. So we want to find out the frequency at which the second order function, it's a second order function, and we want to find when the g of j omega is maximum. So how to find out? We're just considering this, so denominator. So when g of j omega is maximum, that means the denominator is minimum. Okay, that means f of omega. So we are finding, so we are differentiating it and making it equal to 0, and we came to this value. This is very important for second order function, resonant frequency. Okay, and what we observed is when zeta is between 0 and 1 by root 2, okay, this is valid. Okay, so above zeta you'll get this omega is, so at omega equal to 0 you'll get the maximum peak. Okay, but we are not concerned about it. So when the system is underdamped and the zeta is between 0 and 1 by root 2, so this definition is valid, resonant frequency. Okay, at this particular frequency you'll get the maximum magnitude of the g of j omega. Okay, so that we have seen here. Okay, so what is the maximum magnitude? So if you put omega equal to omega r, you'll get this maximum frequency, maximum magnitude, which is 1 by 2 of zeta into root of 1 minus eta square. Okay, and we have seen if we increase or decrease the value of zeta, what will be the effect on the magnitude plot. Okay, so this is the effect you can see here. Okay, if zeta increases, so you can see here, okay, we are going, the error actually decreases if we go downwards. Okay, and also the frequency also is moving on the left hand side. Okay, so we have seen this, and what we have seen is a definition of minimum phase system. Okay, so we have considered two systems, so g1 of s and g2s. Okay, so what is the difference? The only difference is you have a negative 1 minus ts. Okay, that means you have a 0 on right hand side. So that is the difference. And if you see the magnitude, so magnitude is same for both of them. Okay, if you see g1 and g2 magnitude, so magnitude wise there is no difference, but if you plot, if you get the phase, so for the phase, for if you see the phase of g2, you'll get minus 180. So that's why we are calling as minimum phase system. Okay, because of that minus denominator, sorry, no, numerator 1 minus j ts or 1 minus ts. Okay, so up to now, up to here we have studied Bode plot. So any doubt in the theory part? Anything you want to ask? Okay, we'll go to the tutorials. So first few questions are very simple, so you can answer them, okay, directly. So I'll read the question. In the y-axis of the magnitude plot of the Bode plot, the magnitude of sinusoidal transfer function p of j omega is expressed at. So you know it should be expressed in dV. Okay, so if we have this transfer function, is a sinusoidal transfer function, so how to take the magnitude? Okay, this is how you represent the magnitude. And if you want to plot in the Bode plot, so that has to be in dV. So what you take, okay, you take log of it and multiply by 10. So log is of the base 10. Okay, so this is how, so this quantity now is in dV. Okay, so this is what is asked in the question. In the y-axis of the magnitude plot of Bode plot, the magnitude of sinusoidal transfer function. Okay, so this is how we'll be representing the magnitude. So first is very simple. Okay, so second is correct. Okay, I hope there is no doubt. Okay, and second question is, which one of the following is not correct about using log scale for plotting frequency in the Bode plot? Okay, a larger range of frequency can be represented, so this is true, right? Because that is the reason we are taking the log scale. And the second option is the lower frequency ranges can be expanded. This is also true. Okay, so this is also one of the benefit of using log scale. Okay, so these two are true. And the third option is zero frequency can be represented. So you cannot represent zero frequency, right? because we are taking this log of omega. Okay, so if you plot log function here, so how the log function will be like, so you see at 0 it tends to infinity. Okay, so that's why you cannot, so this value is what, 1. Okay, this is like log of omega. Okay, so that's why we will not represent a zero frequency. Okay, we can represent very small frequency 0.001, but will not be representing zero frequency on the log scale. So this statement is wrong. Okay, uh, because it's not defined at omega. You can see from the plot also. Okay, the last point is, if point C is exactly halfway between A and B, the value of frequency at point C is geometric mean of corresponding value at point A and B. Okay. So it's like, it's what it's saying is this. So A and B, so we have point C. Okay, if point C is exactly halfway between point A and B, okay, the value of frequency at point C is geometric mean of corresponding point at A and B. Okay, so what we can see is, this is A, let's call this omega, and this is what, omega by 2, and this is 2 omega. Okay, so what is this? This is on the linear scale, right? So in the linear scale, what I'm showing is this. So this point C frequency is this, geometric mean is omega by 2 into 2 omega. So this will be equal to omega. This is linear scale, right? So if you take the logarithmic scale, okay, so what you'll get, I don't get the point here. Point C is exactly halfway between point A and B. The value of frequency at point C is, okay, I think, okay, I'm not getting this last point. Okay, so this is valid for the linear scale. We will see for the log scale also. Okay, see the next question. Okay, if the plant transfer function is expressed as this, the magnitude of the plant sinusoidal transfer function is, so let's call this as P of S equal to G of S. And how to find a sinusoidal transfer function? Okay, so this is how we find out. Okay, G of J omega. And if you want to find out the magnitude, okay, so magnitude is magnitude of numerator by magnitude of denominator. Okay, and in dB this is, okay, base of 10. If you take log of this, okay, so how this can be represented, because this is log, right? So 20 log of 10 J omega, okay, minus 20 log of 10 G of J omega. So this is also the reason why we are taking the log. Okay, so in this, if you see the options here, first option is wrong, second is also wrong, because we are getting minus here because G of J omega is in denominator. Okay, so this last option is correct. So this is also very straightforward question. I hope there is no doubt. Already we have seen in the theory. Okay, so in problem 3, the phase of the plant transfer function. So phase of plant transfer function, that means, okay, let me just copy this. Okay, so you want to find the phase. So this is equal to, very simple, phase of j omega minus phase of j omega. So that is one of the advantage. Okay, directly we can get the phase. Okay, so which option is correct here? So we don't take the log here. Okay, so this is correct, right? Because g of j omega was in denominator, that's why minus sign. Okay, I hope there is no doubt in this case also. Simple question. Fifth is consider ps equal to 10. Okay, ps is 10. Okay, the magnitude in dB and phase in degree of the corresponding sinusoidal transfer function are respectively. So if you want to find sinusoidal transfer function, you put p s equal to j omega. Okay, then also because it's a constant, so which is equal to 10, so we have to find the magnitude in dB. So how to find out? So which will be 20 log of p j omega. So if you find the magnitude of this, which will be equal to 10, because we don't have omega, right? Only constant term. So 20 log of base 10. Okay, so which is equal to, so log of 10, okay, base is 10, so that's why it will be equal to 1. Okay, so this is in dB. Okay, it's 20 dB. So magnitude is 20 dB, and we have to find the phase also. Okay, you know phase of j omega. So you know this is 10, right? So 10 means 0 degree, just a constant. So you see. Okay, so magnitude is 20 dB and the phase is 0. Okay, so third option is correct. Okay, suppose if we have ps equal to minus 10, then we could have said the phase is minus phase is plus 180 degree. Okay, magnitude remains same. Okay, 10. Okay, doubt in this case? Any doubt you have?
Angle is 0 degrees.
Yes.
Angle is 0 degrees. Can you please explain? I didn't understand.
Okay, so it's like just a constant, right? If you have a constant, so you can, in Cartesian you can see a plus jb, right? Any value like s equal to a plus jb. Okay, here also we are taking a plus jb, but we are not taking a. Like let's assume like this, s equal to a gb. Okay, so really only if you want to find the phase, let's find the angle for this. How you find it? B by j, right?
Yes,
So
yes, sir, understood.
like it is p of s, just constant we have. Omega is also not there. Okay, so if you see b is equal to 0 in this case, so that's why 0. Okay, so I'll write this. It's like tan inverse of 0. That's why I'm calling it 0. Imaginary part is not there. Okay, so that's why 0 degree. Okay, the slope of the magnitude plot of 1 by j omega. Oh, you have to find the slope. Okay, so we are given with this function. Okay, so what is the magnitude? How to find the magnitude of this? Which will be equal to omega, right? Because what you will do, real part square plus imaginary part square. Real part is equal to 0, which will be omega square. Okay, so directly I can write 1 by omega. Okay, and we have to find in dB, right? So 20 log of p j omega. So this will be in dB. So it will be 20 log of 1 by omega. Okay, so just elaborating it. Okay, so this will be equal to 20 log of 1 minus 20 log of omega, right? And 20 log of 1 will be equal to 0. So that's why this will be 20 log of omega. Okay, so this is base 10, log is 10. Okay, so it will be 20 log of base 10 omega. Okay, so this is in dB, right? So this is in dB. So just now we have found out the magnitude and we want to find the slope. So what we do, we go one decade above. Okay, let's see what is the magnitude at omega equal to, sorry, we will check the magnitude at 10 omega. Okay, so what is the magnitude? Let's find out. So it's like P, what we are doing is P J 10 omega. We are finding the magnitude and that too in dB. Okay, so minus 20 log 10 omega. Okay, so which will be equal to 10 minus 20 log of 10 omega. Okay, so this is equal to how much? So log of 10 is equal to 1. So minus 20 minus log. Okay, so this is the magnitude. Okay, so this is the magnitude at 10 omega, but what we can see is now the magnitude has decreased by minus 20 dB. Okay, if you just compare these two values here, so this is the magnitude at omega. Okay, and this this is the magnitude at 10 omega. Okay, so what is the difference? So difference is this minus 20. So now the magnitude has decreased by 20 dB. Okay, so what if you plot the magnitude plot? Okay, so that's already we have seen in the, so this is P of j omega. So this is in dB. Okay, so this is in dB and omega. Okay, so omega and 10 omega. So what we are seeing, let's suppose we have some magnitude at omega, but at 10 omega, so now the magnitude decreased by minus 20 dB. Okay, so let's assume that here the magnitude was 0 dB and now the magnitude is minus, not 0 dB, some okay, let's not go into this what is the magnitude, but you get it, right? The magnitude decreased by 10 d 10 20 dB in 1 decade. Okay, so this is 1 decade, right? And this is 20 dB. So what we can say, the slope is minus 20 dB per decade. Okay, so this is the slope. Okay, so they're asking slope, the slope of magnitude in octave they are finding. Okay, we have to find in octave. So what is octave here? So octave is, sorry, I have calculated for 10 omega. You calculate at 2. Now you calculate the magnitude at 2 times of omega. Okay, I'm just doing it in red. So again minus 20 log of 2 omega. Okay, so which I can write as 20 log of 2 minus 20 log of omega. Okay, so this will be, if you find log of 2, okay, into 20, if you do, this will be I think minus 6. Minus 6 into minus 6 minus 20 log 10 omega. Okay, now we have to compare like these magnitudes at omega, this magnitude, and at 2 omega. So you can see now the magnitude has decreased by minus 6. Okay, so if I draw the same, okay, so what is happening? So this is at omega and at 2 omega. Okay, so this is omega and this is P of j omega in dB. Okay, and this is 6 dB. Okay, and this is 1 octave, right? So that's why the slope is minus 6 dB per octave. Okay, same thing. Okay, so the frequency is, so the slope is minus 6 dB per octave. Okay, any doubt? So I found in decade also minus 20 dB per decade, and in octave minus 6 dB per octave. Okay, for decade I found the magnitude at 10 omega, and for this I have found at 2 omega. Okay, you can write like this, J of 2 omega. So this is in dB. Okay, any doubt in this question? Pretty straightforward. I think we have seen in the theory part also for this function 1 by s. Okay, same thing we are doing here. Okay, I'll go to the next question. The corner frequency of transfer function. Okay, so what is the transfer function? 2s plus 1. So we have studied this general form, right? So I'm writing the general form, ts plus 1. Okay, so we have seen, so from, if you just compare these two transfer function, t is equal to 2, right? And also from the theory part, if we recall, so the corner frequency was at omega equal to 1 by t. Okay, but I will do in detail. Okay, so we have to find the corner frequency. So what is the sinusoidal transfer function? If you put s equal to j omega, that would be, okay, this will be j of 2 omega plus 1. Okay, so just replace s with j omega. And how to find the magnitude? It will be equal to 1 by 2 omega whole square. So it's like real part square plus imaginary part square. Okay, it's like this. So I am just writing like this, 1 plus 2 omega square. Okay, I hope there is no doubt in this. Okay, so let's find in dB. So 20 log of this value. Okay, so you know log, this is 1 minus 20 log of this. Okay, let's not do it. Okay, let's find the low frequency and high frequency asymptotes. Okay, so let me first find the low frequency asymptote. Okay, so in low frequency asymptote, what we do, omega is, like omega is very low, it has very less value. Okay, so what we take, typically it's less than 2. Okay, like 1 by 2. Okay, so if you compare 1 and 2 omega, okay, so if you compare these two values, this will be very small. Okay, so we can neglect in terms of 1. Okay, so it's like 2 omega is very less than 1, right? So that's why we can neglect that. So what will be the magnitude? 20 log of 1 by root 1. Root 1 is 1. Okay, so that's why the low frequency asymptote is 0 dB. Okay, so let's find the high frequency asymptote. Okay, now we have a different case where 2 omega is much greater than 1. So we can neglect 1 in terms of 2 omega, right? So how the magnitude will look like? 20 log of 10, 1 by root of 2 omega square. Okay, so we have neglected 1 in terms of 2 omega. Okay, so this is how. So it will be equal to 20 log of 10, 1 minus, so I'm just writing it. Okay, this will be what? 2 omega. Okay, because what you can write like this, 1 by 2 omega, right? Square root and square, you get cancelled. Okay, 2 omega. So 20 log of 1 is 0, so 20 log of 2 omega. Okay, So this, we have just now found the high frequency asymptote also. Okay, and what we have to find out, we have to find out the corner frequency. Okay, so corner frequency is when these two asymptotes will intersect. Okay, so you see, when the high frequency asymptote will meet the low frequency asymptote. Okay, when when they will meet, when for what value of omega this will become 0 dB. Okay, then only the two will meet, because low frequency asymptote is equal to 0 dB, right? So we have to find out the omega at which you will get 0 dB. Okay, so you can see clearly when omega is equal to 1 by 2. Okay, when omega is equal to 1 by 2, what you will get at higher, if you put this, you will get 2 into 1 by 2, right? So it will be minus 20 log of 1, which will be equal to 0 dB. Okay, so at omega equal to 1 by 2, magnitude is this. Okay, so at omega equal to 1 by 2 radian per second, higher frequency asymptote is intersecting the lower frequency asymptote, low frequency asymptote. Okay, so this is the corner frequency. Okay, so that is the definition, right? So at what frequency these two asymptotes are meeting? So they are meeting at omega equal to 1 by 2. So you just, so I have highlighted the high frequency asymptote magnitude, right? So just just see what value of omega you find the magnitude to be equal to 0 frequency asymptote, that is equal to 0 dB. Okay, so at omega equal to 1 by 2 you will get 0 dB. So that is the corner frequency. Okay, so corner frequency is equal to 1 by 2.5 radian per second. Okay, and directly also we can find out. So how to find directly? Okay, so it is in the, you write in this form. Okay, ts plus 1, and you know the corner frequency is equal to 1 by t. Okay, so in our here, if in our example t is equal to 1 by 2. Okay, directly you can say the frequency is 1 by 2. Okay, and because what you will see when I am doing this, let's plot the magnitude and the magnitude plot. Okay, so this is the magnitude plot with respect to frequency. You will see, so what we have seen is at 1 by t, so initially at 0 frequency asymptote what 0 dB. Okay, so this is, okay, so this is in dB. Okay, so this is 0 dB. Okay, at 1 by t, so what is happening, it will decrease. Okay, so you have seen how it is decreasing like this. Okay, so this is the corner frequency. Okay, so that's what we have calculated. So t was equal to 2, so omega is equal to 1 by t. Okay, okay, and its slope is what, minus 20 dB per decade. So how to find the slope here? Okay, simple. This we know at high frequency asymptote the magnitude is this minus 2 log of 2 omega. Okay, you just take 10 times of that frequency. Let's take 10 omega. Okay, so this is one magnitude. Let's take at 10 omega, so 2 into 10 omega. So what you'll see is, you can write in this form 20 log of 10 minus 20 log of 2 omega. Okay, so this is what, this is minus 20. Okay, 2 omega, and what you can see is just compare these two values. Okay, magnitude at omega and magnitude at 10 omega. So what is the difference? Now you see the magnitude has decreased by minus 20 dB. Okay, so that's why I'm writing now the slope is minus 20 dB per decade. And when the slope starts decreasing, it starts decreasing at corner frequency. Okay, so this is okay. So this is low frequency asymptote. Okay, so you can see the magnitude is equal to 0 dB, and this is high frequency asymptote. Okay, and they are intersecting at this point 1 by t. That's why we are calling this as corner frequency. Okay, I hope there is no doubt. Just see in case you're not understanding anything. Okay, straightforward, you could have found out omega c is equal to 1 by t, but we know what is that corner frequency where the two asymptotes are meeting. Okay, okay, so I'll go to the next question. So question 8, the magnitude in dB of the sinusoidal transfer function corresponding to problem 7 as the frequency tends to 0. So already we have calculated this. Okay, so it's we have to find the low frequency asymptote. Okay, frequency tends to 0 means that this value. Yes, because frequency is very low now, and we have to find the magnitude at that point. Okay, same answer. See, the magnitude in dV of sinusoidal transfer function corresponding to problem 7 as the frequency tends to 0. In this case also, frequency is very almost tends to 0. Okay, omega is very less than 1 by 2. Okay, so what is the magnitude? That is equal to 0 dB, right? Oh, so what is the answer? 0 dB. Okay, so if you want to see the magnitude plot, okay, let me just copy this. Okay, so what it is asking is the magnitude here. Okay, so you can see as omega is tending to 0. Okay, what is the magnitude? Magnitude is equal to 0 dB. Okay, you can see from the graph also. Already we have found out by finding the low frequency asymptote. So any doubt in this case? Okay, we go to the next question. The phase of sinusoidal transfer function corresponding to problem 7 at corner frequency. We have to find the phase at corner frequency. Okay, so what is our transfer function? 1 by 2t plus 1, sorry, 2s plus 1. Okay, so sinusoidal transfer function is 2. Okay, it's okay, so I'll write in this form j of 2 omega plus 1. Okay, and I have to find the phase of this. So how to find the phase? Okay, so phase of numerator, you see just a constant. Okay, so the phase is 0 degree minus tan inverse of 2 omega by 1. Okay, so I can write only 2 omega, right? Imaginary part by real part. Real part is 1, imaginary part is 2 omega. So this is the phase minus tan inverse of 2 omega. Okay, so in the question we have to find the phase at corner frequency. So in the previous questions we have found out the corner frequency is 1 by 2 radian per second. Okay, so let's find the phase at 2. Okay, 1 by 2, sorry. Okay guys, 1 by 2. Just tan inverse of 2 into 1 by 2. So tan inverse of minus tan inverse of 1. So you know that is equal to 45, right? Tan inverse of 1 is 45 and minus of 45. So we have calculated the phase at corner frequency. Okay, minus 45. I think this is also very simple. Okay, so you know how to find the phase of a transfer function. Okay, so individually you find the phase for numerator and denominator. Okay, so in our case the numerator is equal to 1. So you know the phase, if you find the phase of 1 or any positive value, that is equal to 0, and for the denominator the phase is if you tan inverse of imaginary part by real part, but that is in denominator, that's why minus sign. Okay, so the phase is minus tan inverse of 2 omega, and at corner frequency, so corner frequency is 1 by 2. Okay, so if you put 1 by 2 in this, minus tan inverse of 2 into 1 by 2, we'll get minus tan inverse of 1, which is equal to minus 45 degree. Very simple. Okay, so the answer is minus 45 degree. Any doubt in this question? Okay. So let's find the phase of this particular transfer function. Okay, so just now we have found the phase at corner frequency. Okay, so if you try to find out the phase at different, so this is the, if you just consider this. Okay, so at lower frequencies, at omega closer to 0, so what you will see is the phase is equal to 0, right? So let me just say 0 is here, so 0 degree, and we have found out this is equal to minus 45. Okay, and if you put at omega means at larger value of omega, you can put omega equal to infinity. So what is minus tan inverse of infinity? So tan inverse of infinity is 90 degree, right? So minus tan inverse of infinity will be minus 90 degree. Okay. So this is how the phase will look like. Okay, so I have drawn the phase also. Okay, so this is the corner frequency. Okay. So any doubt in this case? I hope there is no doubt. Okay, simple question. So additionally, I have drawn the phase plot for this transfer function. So let's see. Okay, then we have to find the corner frequency of transfer function. Okay, so we have a numerator only transfer function 2s plus 4. Okay, here also the simplest technique you can write. So we have studied like this form, right? Ts plus 1, right? Ps equal to ts plus 1. Okay, so what we have seen here, the corner frequency was equal to 1 by t. Okay, that we have seen. Here also you can write in this form itself. So let's just take 4 common. So what you will get, 2 by 4 s plus 1. Okay, this is 4 into s by 2 plus 1. Okay, so this we can treat as constant, so it is like k into ts plus 1 form. Okay, but corner frequency is what? Here also corner frequency is, okay, let me write in green here, 1 by t. Okay, so just compare for this transfer function. Omega is equal to, okay, t is 1 by 2, right? So it is like 1 by 2. Okay, it will be 2 radian per second. Okay, just comparing, we can see straightforward answer. We don't have to find the low frequency asymptote and high frequency asymptote. Okay, so but let me find that also. So first, what we do, find the sinusoidal transfer function. So it will be 2 of j omega plus 4. Okay. And how to find the magnitude? Okay, so real part square plus imaginary part square. So this is the imaginary part. Okay, so this is how the magnitude is. So, and if you want to find the magnitude in dB, what you do, you take the 20 log of magnitude. So this is the magnitude in dB. Okay, so let's find the low frequency asymptote. This is asymptote of magnitude. Okay, low frequency asymptote. What we do here, okay, omega is very, it's close to 0. Okay, so what we want to do is we want to neglect omega, 2 of omega in terms of 4. Okay, so I'll just write, I will neglect that, like 4 square plus 0 square, omega is close to 0. Okay, so this is the low frequency asymptote. Which is 4 square, what is 4? Okay, so it is like 20 log of 2. So you can write 4 as 2 square. Okay, and you know 20 log 2 is 6. This is, let me write in this way, 20 into log 2. This you know is equal to 6. Okay, this will be 12 dB. Okay, so this is 12 dB, and let's find the high frequency asymptote. So what you do now, this term is very much larger than 4 square. Okay, so we are talking about very high frequencies. Okay, so what we can do is we can neglect 4 square in terms of, if we compare to omega whole square. Okay, so let's do it. So after neglecting, what you'll get is 20 log of 2 omega square. Okay, so this is at very high frequencies. So this will be 20 log of 2 omega. Okay, so we have calculated the magnitude. Okay, so low frequency asymptote and high frequency magnitude. And what we can see here, so when this magnitude becomes equal to 12 dB, that is our corner frequency. Okay, so when these two asymptotes intersect, that's the corner frequency. So you can find out by just equating them. Okay, so directly we don't need to find, oh, okay, mathematically is like you first you do 12 by 20, then what you do, this is 10 raised by 12 by 20. Then what is omega is this. Okay, that is separate thing. Okay, so easy thing is what, just see this. Okay, and if you see here this value, change the color. Okay, 20 logs 2 square and 20 log 2 omega. Okay, so what should be omega? You can write 4 as this also, right? 20 log 2. Okay, we have to compare these two values. Okay, so you can see here, if we put omega equal to 2 radian per second, okay, what you will get? If you put here omega equal to 2 radian per second, if you put, you will get the value as 12 dB. Okay, you're getting it. So at what omega you'll get 12 dB. That's what we are trying to find out. And at omega equal to 2, you'll get 12 dB. Okay, so that is what the corner frequency is, right? So just calculate this also, we'll get the same thing. 10 raised to power okay, this I'm getting is some 1.99. So this is like 2 radian per second. Okay, but we know if we place omega equal to 2 omega in high frequency asymptote, I will get the 12 dB, right, from this simple. So this is the corner frequency, and the easiest part also we have seen directly. Okay, so the answer is 2 radian per second. So any doubt in this case? So first is like directly you can see from the transfer function, and you write the transfer function in this form, ts plus 1. Okay, so you know what is t, and just 1 by t is the corner frequency. Okay, and long form is this, you find the low frequency asymptote and high frequency asymptote, and you see where they interact or where they intersect. Okay, so in high frequency asymptote magnitude value, you just see at what value of omega you'll get 12 dB in this case. Okay, so we are seeing it, we are seeing that at omega equal to 2 radian per second we'll get 12 dB. So that is the corner frequency. Okay, so any doubt in this case? Okay, we'll go to the next question. So the magnitude in dB of sinusoidal transfer function corresponding to problem 10 as frequency tends to 0. So already we have calculated, right? So this, okay, so we have found the magnitude when omega is very small. Okay, so that's what it's asked in the question, as the frequency tends to 0. Okay, so this is the magnitude, right? 12 dB. So any doubt? So let me draw the magnitude plot also for this transfer function. So it is in dB, right? So this is at omega 2 radian per second. Okay, so this will be plus 20 dB per ticket, and this is the corner frequency. Okay, and this is what 12 dB. Okay, so it is constant up to corner frequency, and then the magnitude, what is the value of magnitude? Then it will be plus 20 log 2 of omega. Okay, this one. And how it is plus 20? Okay, so if you see this, okay, let's find what is the slope for this. How to find the slope for this? At higher asymptote, you know the magnitude is equal to 20 log of 2 omega. So let me check it once again. So at where it is, yeah, 20 log of 2 omega. Okay, so you take a frequency 10 frequency at 10 omega. Okay, so this is the magnitude at 2 omega. Let's find the magnitude at 10 2 into 10 omega. Okay, 10 times more. So what is the frequency, what is the magnitude? You will get 20 log of 10 plus 20 log of 2 omega. Okay, so this is what 10 log of 10 is 1. 20 plus 20 log of 2 omega. Okay, just compare these two values. So this is the magnitude at omega, some omega. Okay, so I'm not saying like omega greater than 2 radian per second. You can take omega equal to 2 radian per second also. And we are finding the magnitude at 10 times more. Like we are finding 2 into 10 is 20 radian per second. So you'll get the magnitude this. That means your magnitude has now increased by 20 dB. So that's why the slope is plus 20 dB per decade. Okay, I hope there is no doubt. Similar to what we have been doing in the previous question. Okay, so in this case, the answer is 12 dB. Okay, I hope there is no doubt. Simple question. So the phase of the sinusoidal transfer function corresponding to problem 10 at the corner frequency. Okay, this is the transfer function 2s plus 4. Sinusoidal transfer function is this. Okay, and we have to find the phase. How to find the phase? So only numerator is there. Okay, so this will be tan inverse of 2 omega by 4, which is tan inverse of omega by 2, right? And we have just calculated the corner frequency 2 radian per second. Okay, so let's find the phase at 2. So it is 1 by 2. Sorry, this is 2 by 2, right? Omega is 2. 2 by 2 is tan inverse of 1. Just plus 45 degree. Okay. So answer for this is second low. Let's also plot the phase plot for this transfer function 2s plus 1. Okay, so what is required for this? We have this information, right? So let's plot it. With respect to frequency. Okay, so this is corner frequency, so this is equal to 2 radian per second, so it is equal to 45 degree. But if you see, when omega is very small, okay, close to 0, if you put tan inverse of 0, what you'll find out? So tan inverse of 0 is what? 0 only. So the angle will be, so the frequencies which are closer to 0, very small frequencies, your phase will be equal to 0 degree. Okay, and at omega it is equal to 45. Okay, So this is not 0. Okay, let me draw it here. 0 is here. Now 45 is here. Okay, and at very high frequencies, omega tending to infinity. Okay, let's say it's very high because we are taking the assumed terms here. So if you put tan inverse of omega, what you will get? Tan inverse of infinity is equal to 90 degree. Okay, so this is how the phase plot will look like for this transfer function. Okay, so which is opposite to what we have drawn previously for the this case. Okay, it's going from 0. Initially the phase is 0 degree and it is shifting to minus 90 degree. Here from 0 degree to plus 90 degree it's going. Okay, you see that was, this is 0 case. Okay, 0 in the sense ki 2s plus 4. Okay, so if you consider a transfer function which consists of zeros and poles, so it does not have any pole, right? So this is the effect of a 0. Okay, so the answer is plus 45 degree. I hope there is no doubt in this question. Okay, let's go to the 13th question, which says consider a plant whose transfer function is this. The magnitude of low frequency assumed tort in magnitude plot of the corresponding sinusoidal transfer function is. Okay, so we are given with this second order plant. Okay, so sinusoidal transfer function is, you put s equal to j omega. Okay, so what you'll get will be minus, okay, minus omega square plus 9. So I can write 9 minus omega square plus j 3 omega. Okay, so what is the magnitude? Magnitude is 1 by imaginary part square plus, sorry, real part square plus imaginary part square. This is the magnitude. And if you want to find the magnitude in terms of dV, what you do? Okay, this will be minus 20 log of, or let me just write first 20 log of 1 by this. Okay, so this is in dB. Okay, so in the question what is asked, you have to find the low frequency assumed. Okay, so omega is very small. Okay, so here omega is very small, like closer in terms of it can turn to 0, what we say. Okay, so how to find this? You just see this first. Okay, 9 minus omega square. So you know omega is very small. So if you compare it with 9, its value is negligible. 9 minus very small quantity you're subtracting. So it will be equal to 9 itself. Okay, and plus 3 omega square. So again, if you compare it with 3 omega square also, because omega is very small and you are squaring it. In the previous case also you are squaring it, and that's why the value even decreases further. Okay, so we can actually neglect the omega term. Okay, so we are taking the assumption where omega is very less. So if you want to take how small this is like, okay, let me say Okay, let's do this way only. Okay, so any doubt in the here up to now? We're just comparing individual terms. So I'm initially what I had done, I'd compare omega square with 9. Okay, so it's our assumption that omega is very small and omega square is further very smaller value. So if you compare it with 9, you will get 9 minus very small value. So we'll say let's ignore omega square. So 9 minus omega square, it's tending to like 9. Okay, again if I compare with this term 3 omega square, again the same comparison. 9 you are comparing with 3 omega square. Okay, omega is very small, so that's why we came to this. So this can be written as 20 log of 1 by 9. Okay, so what we can do will be, so you can write 20 log of 1 minus 20 log of 9. Okay, so we have to find this. So 3 square, like 20 into, you can write 3 square into log 3. Okay, minus 40 log of 3. So what is this value? So log of 3 is equal to 0.47. Multiply by 40, you will get 19.08. I am getting TB. Check. Okay, 19.1 is close to my answer. Okay, so let's check this. Okay, so we are asked with low frequency asymptote. So at omega, very small values of omega, we have to find the magnitude. Okay, so what I have done is I have just removed the omega square terms. Okay, so I will be ending up with the 20 log of 1 by 9. Okay, so 20 log of 1 by 9 is equal to minus 19.08 dB. I hope I'm doing all the calculations correct. Any doubt in this case? Okay, we'll go to the next question. Okay, problem 13, the corner frequency of the sinusoidal transfer function. Okay, sinusoidal transfer function. So also, like, directly we can find out. So this is the transfer function. So that first I'll show you how we can directly find out. So 1 by s square plus 3s plus 9. Okay, so it is like in this form, right? Square plus 2 zeta omega n s plus omega n square. Okay, and we have seen in the while we are uh, studying the theory part, so the corner frequency was what? Equal to natural frequency, right? This was equal to corner frequency. So here also we can see, like, if you just see omega n, in this case natural frequency is equal to 3. Okay, 3 radian per second, and you can say that is the cutoff frequency. Okay, but let's just calculate it. Okay, so how to calculate? So we have just now found out the low frequency asymptote. Also in this question we should find out the high frequency asymptote, and we'll see where they will intersect. Okay, so I know this thing generalized. So So this is the magnitude. Okay, so I want to find the magnitude when omega is very, very large, close to infinity. Let's find out. Okay, so what you can see for very large values of 1 omega square. So you know the first term will be omega square because I am neglecting 9 as compared to omega square. Okay, so this will be there. Okay, so 20 of log. So what I can see if I just compare these two now, because one is omega raised to power 4 and other is 9 omega square. Saying omega raised to power 4 is much greater than this value. Okay, one more approximation I can do. So I'll get in terms of, this is root of omega 4. Okay, this is assumed truth, right? So which is equal to 20 log of 1 minus 20 log of, so I'm writing in this way, so omega square. Okay, so this is equal to 0, so I'm left with 20 into, so I can take this to here, log of omega minus 40 log of omega. Okay, so what is the low frequency? Okay, so let me write this as, because we'll be comparing these to asymptotes, right? 20 log of 9. Okay, so here let me not, okay, let me just compare this value minus 20 log of omega square. Okay, so we have this magnitude at high frequency asymptote is what? Minus 20 log omega square, and at low frequency what is the magnitude? Minus 20 log of 9, this value. Okay, and this is constant, right? At low frequency, if you see low frequency range, this magnitude is constant, and at higher frequency we got this, and at what we have to find out the frequency at which these two becomes equal. Okay, you can clearly see if you this magnitude and this value written in red color. So you can see if I put omega equal to 3, these two magnitude will be matching, right? So at omega equal to 3 radian per second, so what is the magnitude? Minus 20 log of 3 square, which 3 square is what? 9. Okay, so what we can say, omega equal to 3 radian per second is the corner frequency, right? Already we know, like, okay, that is equal to the natural frequency, right? But we have seen the intersection point, right? So at this point these two asymptotes intersect. Okay, that's why we are calling this as corner frequency. Okay, so you can match these two values. So the answer is what? 3 radian per second. So any doubt in this case? Okay, let me make space and also write low frequency as input here. So this is the high frequency and this is the low frequency, and you have to compare the magnitude to get the corner frequency. Okay, so this is the magnitude. Okay, so if we can compare these two magnitudes, you'll get the corner frequency, which is coming out to be 3 radian per second. Okay, and what we are seeing here is, so if you, and eta, what you're getting here, if you compare to 2 zeta omega n with 3, and you know omega n is 3, so zeta is 1 by 2.5. Okay, so roughly I will draw the magnitude of the transfer function. So this is in dB. Okay, omega n equal to 3 radian per second. Okay, so initially what is the magnitude? Minus 19.01 or 19.08. So it is like this. This is the approximate drawing I'm drawing. Okay, so the slope will be minus 40 dB per decade. So that we have seen also. Okay, so this value is 19.1 dB. Okay, and this is the corner frequency. Okay, so actual will be different. Okay, actual will be like this. We'll have some, so this will be resonant frequency. Okay, so like this. Okay, so this is how the second order, the magnitude of second order function looks like. So any doubt in this case how we got to the corner frequency? Okay, let's do the next question. Next question is in problem 13, the resonant frequency of sinusoidal transfer function. So you know the formula, right? First we will do with the formula. What is that? I hope this is correct. Okay, and we know because zeta is also 1 by 2. Okay, which is equal to 0.5. So this is in the range of 0 to 0.707, 1 by root 2. Okay, so let's find out. You know omega n is equal to 3, 1 minus zeta square, which is 1 by square. This is 1 minus 1 by 2 is 0.5, right? So 3 into root of 0.5. So what you'll get, if you find the root of 0.5, you will get 0.707. Okay, it's like 1 by root 2 into 3. 12.12. It's like you are doing like this. Okay, so that's why what we can say, this frequency is omega r, or omega r is coming to be 1.12 radian per second, which is less than natural frequency, right? So let me write this way, this will be more clear. It is like 2.12 radian per second. Okay, so where the magnitude is the highest. Okay, okay, so what is the other way how we used to calculate this? Okay, so the long way is this. So we have this p of j omega is what? Let's find out. So let me copy the original magnitude. Okay, this one. How we got to this, I'm just explaining that. Okay, so okay, so what we used to do at resonant frequency, this is maximum, right? This is maximum. That means what we want, the denominator term should be minimum. So it should be minimum. Okay, let me call this as f of j omega. This term should be minimum. Okay, so how to find at what frequency this is minimum? We have to find out that now. So let's, this is the magnitude. Okay, it is like 1 by f of j omega. Okay, so let's differentiate this with respect to omega. So what you'll get, 9 minus omega square. Okay, this is minus 2 omega plus 3 into 3 omega into this 2 into 3 omega into 3. Okay, so and it should be made equal to 0. Okay, let's find out at what frequency this is equal to 0. Okay, so this is minus 4. Okay, let me write like this. It's 2 into 2 minus 9 minus omega square. Okay, into omega plus 2 into 3 into 3 omega equal to 0. Okay, so one, if you just cancel this, what you'll get, omega equal to 0. Okay, so this is at this one particular frequency. So let's find what is the other value of omega. So to find that, what you'll get, minus 2 into 2 9 minus omega square. So if I just take it on that side, what it becomes positive, so it's just equal to 2 into 3 into 3. Okay, and we have to solve this to get the value. If I am doing everything correct. So it's 9 by 2, and to find omega square, what you have to do, 9 minus 9 by 2. It's like 18 in minus 9 by 2. So it's 9 by 2. Omega square is 9 by 2. Okay, and what should be, this is 9 by 2. Just 4.5. Root of 4.5, right? And root of 4.5 is what? I think you'll get 2.2. So 2.12. Okay, so and again, how to check this is minima? You again double differentiate this f of j omega. So what is the original value? Again, if you, I'm not doing it, so what I'm saying is you just do differentiation of this. Okay, so your value should be greater than 0 because we are finding the minima here. Okay, it should be positive, right? You'll find out that this will be positive, so we can say this is the resonant frequency. Okay, so we have seen the procedure in the lecture also. Okay, and we got to this value, and what is the peak value if you want to find out? Okay, so this we are finding the at omega equal to omega r. Okay, so directly formula is there. Otherwise, what you can do is you just put this into this. Okay, so you'll get the peak magnitude at resonant frequency. Okay, which will also match with the, I think, what was the peak magnitude formula? If you remember, it was 1 by 2 2 zeta 1 minus zeta square, I think. Let me check the formula. Okay, resonant frequency is this, and the peak magnitude is 1 by 2 zeta by 1 minus zeta square. Okay, so these two will be same. Okay, because the concept is same, right? Because the formula came from the original equation. Okay, so any doubt in this case? So directly we can just see what is the value, and also we have seen what is the how that formula came. Okay, by differentiating the magnitude, and again at particular omega, again you double differentiate and you see whether it's minimum or maximum. Okay, so this is 2.12 radian per second. I hope there is no doubt. Okay, let's do, I think, last question here. So consider system 1 and system 2 whose plant transfer function are respectively. So we have P1 of S equal to S plus 2, S plus 1. P2 of S is equal to 2 minus S, S plus 1. So the, if you see, only difference is like it, P2 of S, it has 1 0 in right hand side, right half plane. Okay, so it's like minimum phase system. Which one of the following statement is false about the corresponding sinusoidal transfer function? Okay, the high frequency magnitude value of the sinusoidal transfer function system 1 tends to 0 dB. Okay, you know the magnitude of both of these will be same. Okay, P of j omega is what? J omega plus 2, j omega plus 1. Here also P2 j omega, 2 minus j omega, it will be uh, j omega, I think 2 minus j omega plus 1, same. So if you find magnitude, will be omega square plus 2 square, omega square plus 1. So if you find the magnitude of second transfer function, same value will get omega square plus 2 square plus omega square plus 1. Okay, and what we have to find out, we have to find out the high frequency magnitude value. So if you find the high frequency magnitude of any of the transfer function, both, because low frequency and high frequency magnitude of both the transfer function will be same. So let's find out. So you have to find in dB. So how to find out? 20 log of 2 square plus 1. Okay, so you know omega, excuse me. Okay, so this is the magnitude. Okay, for high frequency, what you do, omega is very large. Okay, as compared to 1 and 2, it's very large. So you neglect 2 and 1 as compared to omega. So now your magnitude will be 2 of log omega square, and if you see in the denominator also omega square. Okay, because omega square is much greater than 2 square, and in the denominator omega square is much greater than 1. So you can neglect 1 and 2. Okay, so if you see, this is 20 log of 1. You know, log of 1 is equal to 0. Okay, so this will be 0 dB. Okay, so high frequency magnitude is equal to 0 dB. So this is true, right? First statement is true. The high frequency magnitude value of sinusoidal transfer function of system 1 tends to 0 dB. Okay, and let's see the second option. The high frequency magnitude value of the sinusoidal transfer function of system 2 tends to 0 dB. This is also correct, because you see magnitude of both the transfer function uh, are same. Okay, so high frequency magnitude is also same. So in case of second also, it tends to 0 dB. This is also correct. And third option is high frequency phase value of sinusoidal transfer function of system 1 tends to 0. Let's find out the phase of system 1. What is that? Tan inverse of omega by 2 minus tan inverse of omega by 1. I'm writing omega. Okay, so at higher frequencies means omega tending to infinity. So if I put the value, what you'll get, tan inverse of infinity is what? First is tan inverse of infinity by 2 is infinity. You will get 90 degree, right? Tan inverse of infinity is 90. Again, tan inverse of infinity is 90. So you'll get 0 degree. Okay. So omega here is into infinity at higher frequencies. Okay. So it will tend to 0 degree. So third statement is also correct. So let's find out for system 2. Okay, this is for system 1. So let's find out for system 2. Okay, so what is that? 2 minus j omega. Okay, so how to find the, so you know this 2 minus j omega is in which quadrant? So if I see 2 minus j omega, okay, so this is in fourth quadrant, right? Because real is positive and imaginary part is negative, so that's why it's in fourth quadrant. Okay, so it will be like this somewhere here, so it is making an angle this one. Okay, so that angle is minus tan inverse of imaginary by real part. Okay, so for the numerator this is the angle, and for the denominator same, minus tan inverse of omega by 1 is omega. And if you put, okay, so this is, I've shown ki 2 minus j omega is lying in the which quadrant? Fourth quadrant, and this is how we calculate the angle, which is, this is 0 degree. Okay, so minus of, so what is this? Theta is tan inverse of omega by 2. Okay, so if you put omega to be infinity, what you will get? Minus 90 degree. Okay, here also you will get minus 90 degree, so you'll get minus 180 degree, or you can say 180 degree. So last statement is not correct. Okay, so here in this case, at the higher frequency phase value of sinusoidal transfer function of system 2 tends to minus 180 degree or 180 degree. Okay, so we have seen here, so that is a minimum phase that already in the lecture we have seen. So this is wrong.
Sir, in that graph one, I did not understand, sir.
Okay, so okay, this is the transfer function, right?
Yes.
Okay, this is the transfer function, and we are finding the angle individually of this and this, right? So what will be the angle for this?
Is tan inverse omega by 2.
Okay, tan inverse omega by 2. That is, that is the case when both are positive. Okay, you have 2 plus j omega, that's fine, where it's lying in the first quadrant, right? This is the angle. Okay,
Yes.
but what we have is 2 minus j omega. Okay, so in this case,
Yes.
this is the 2. Okay, and omega is somewhere here, negative value, right? So if
Yes.
you find the angle, you'll get somewhere here. So this angle I am finding out. Okay, so what is this angle? If you find tan of theta, it will be uh, imaginary part by real part. So in this case, imaginary part is 2, and this is, yeah, imaginary part is omega and real part is 2. Okay, this is tan theta, right? Theta is tan inverse omega by 2. Since it's lying in the fourth quadrant, that's why this negative sign I'm putting it. Okay, because this is minus theta, right? With respect to 0, it's minus
Yes.
theta. So that's why. So it's minus tan inverse of omega by 2. Also you can do is like, 1 second. What is the value? 2 minus j omega. Okay, let me just, yeah, it is correct. Okay, so if you want to see, you can also take the positive value, then you have to take this 360 minus theta. So what you'll get, if you take positive values, 360 minus tan inverse of omega by 2 minus tan inverse of omega. Okay, then 360 minus, you'll get, this is 90, this is 90. Again you will get plus 180 degree. That is same as minus 180 degree, right? So the green one is like I have taken with respect to 0 positive. Okay, but you see, like if it's lying in the fourth quadrant, you take minus of theta, right? So that's what I have taken, straightforward. So I'm getting minus of 180 degree for the P2. So that's why the last statement is incorrect. Okay, so I have taken all the questions. So okay, so let me go through. So initial questions are very simple, straightforward question in the y-axis. Okay, so someone was asking me like cover 1 to 5 questions. So these are very simple questions. Okay, if you see, we have to find out magnitude plot. Okay, we take in dB. So how you take in dB? 20 log of magnitude. Okay, and the second question is which one is correct here. Okay, so I was not getting the fourth point. Okay, which one of the following is not correct about using log scale for plotting frequencies in the Bode plot? Okay, it says if point C is exactly halfway between A and B. Okay, the value of frequency at point C is geometric mean of corresponding value at point A and B. So this is correct in linear scale also. Okay, so let me take the log of what? 2 omega. So we know the ratios are equal. Okay, so these are the ratios. Okay, I'll check with this. But here one of the which statement was false. Zero frequency can be represented. So in the log scale, 0 cannot be represented. So you can see the log scale here. So at 0 it is not, like it tends to infinity. Okay, so that's why 0 frequency cannot be represented. We take closer to 0 values. And in 3 also, f of g, f of function, f of f by g function was there, and we have to find the magnitude. Okay, so clearly, like we have, if we find the magnitude, we can take the ratios of numerator and denominator, and if we take the log, then log of numerator minus log of denominator. Okay, if you multiply by 20, you'll get in dB. Okay, clearly you see here. And in fourth, you have to find the phase. Again, phase is equal to phase of numerator minus phase of denominator. Okay, that is shown here. And we have a constant function. Okay, so constant function means it's not varying with respect to omega. So its magnitude is 20 log of 10. Log of 10 is what? 1. 20 is the magnitude. And if you see the magnitude, okay, so if you see where it is lying, so this is the 10 value. Okay, so it is making 0 degree. Okay, that's why I've written 10 inverse of 0 degree. Okay, so again the slope of magnitude, again we have seen this type of function. We have to find the magnitude 20 log of this. Okay, and how to find the slope? Okay, we take the magnitude at 10 times of that particular omega. Okay, and we'll see whether the magnitude is increasing and decreasing, and if it's increasing, then it is increasing by what value, and if it is decreasing, then it is decreasing by what value. Okay, so here in this case it was decreasing by 20 dB, so that's why we said the slope is equal to 20 dB per decade. Okay. And in terms of octave, you take omega double that of the present value. Okay, you take omega and you take 2 omega and you find the magnitude, and you will see that the magnitude is for 2 omega, the magnitude is decreased by 6 dB. So that's why minus 6 dB is the change per octave. Okay, so corner frequency directly you can just relate with this generic 1 by Ts plus 1, and you can write. And otherwise what you have to find out, low frequency asymptote and high frequency asymptote, and you see where they are intersecting, that value is the corner frequency. Okay, so I have also drawn here low frequency asymptote and high frequency asymptote, and they will intersect at corner frequency. Okay, same. So okay, this is very simple. And we phase, how to find the phase at frequency. So this is the, once you find out the phase, okay, so just put in the value of omega where you want to find the phase. Okay, and rest are very simple questions. Okay, low frequency here also, cutoff frequency, corner frequency here to find out. Okay, so any doubt you have in any of the questions? Okay, so this week we have just learned the how to plot the Bode plot. So how to use the Bode plot we have not learned. We'll be learning in, I think, week 10. Okay, so we have just seen how to plot the Bode plot for different functions. Okay, so how to use this Bode plot we are not seeing. Okay, that we'll see for the, I think, next week. So if you have any doubt, please ask. Okay, I can see there is no doubt, so I'll end the session for today. So I'll meet you in the next session, that is for week 10 tutorial, okay, on Tuesday. So thank you for attending this tutorial.
Thank you.
Thank you, sir.